Okay, in the first part, we have looked at the derivation of the weak form for the study Stokes flow. Okay, so for the study Stokes situations, okay, we have looked at the weak form. In this part, we are going to start writing the code to solve this problem. That is to implement this finite element formulation for solving study Stokes flow. At this point, the coding becomes more difficult because we have more variables. Okay, so we need to store a lot of data, we need to bootstrap a lot of information. So I thought it would be better I code it everything to avoid any bugs, because like it's easy to make bugs whenever we write codes for complicated problems. So what I am going to do, what I'm doing from this lesson onwards is, so where possible I show the code I code online, I code live, but for complicated problems I code early and then I walk you through the code. So this is what I did for this part, for this lesson. And another thing is, it becomes difficult to maintain the code, okay, as the problems get more complicated. So in order to save the effort that we spend in writing the code, so what we typically do is we create auxiliary functions for various aspects, various ingredients. Like for example, so to calculate the stiffness matrices, we need the basis functions, right, and their derivatives. To calculate the gradient matrix and the divergence matrix, right? So what I'm doing is I'm creating separate functions where we calculate the basis functions and their derivatives and simply call them from our stiffness matrix subroutine. In this way, we avoid the duplication of the code and it is less prone to errors. Okay, so first I'm going to walk you through the calculation of the stiffness matrix. Okay, first we see how we calculate these 4 different plots. Okay, so there are 3, but I say 4 because so we can also take this as KPP. Okay, so we take this as KPP. Of course, it is 0. It is a matrix. Okay, so 0 block. Okay, this is a like matrix. Okay, so KP this is a 2 by 2 block matrix, and here KPP matrix is 0. Like 0 means it has all zeros, and it is helpful to write it in this fashion so that we can easily extend it to other problem, like when we add stabilizations. Okay, so first I'm going to show you the code for stiffness matrix. Okay, I will share the code with you so that you can go through it and make use of it. Okay, so here I have a subroutine, okay, function study, stored, study, stiffness and force. Okay, so to this I pass node coordinates. These are the x and y coordinates of the nodes, node number, that element node connectivity, the viscosity value and force, okay, body force. Okay, these are all the 4 inputs we need, and this function outputs KU, KUP, KPU, KPP, these 4 matrices for each element, and also FU and FP. Okay, so we have FU and we can consider this as FP. Of course, it is 0. Okay, again, if like in the future when we have when we add stabilizations and we have some non-zero terms for FP, so this is automatically taken care. Okay, So, and we have two variables, velocity, which has 2 degrees of freedom on each node, and pressure, which has 1 degree of freedom on each node. Okay, so there are many ways in which we can implement this. Okay, so here for our 4 noded element, okay, we have velocities u1x, u1y at node 1, u2x, u2y at node 2, and so on, and pressure, degrees of freedom p1, p2, p3, p4. So we can store them in various fashions. Okay, so one way is like what I'm showing here. So we store all the velocity degrees of freedom together, and then all the pressure degrees of freedom together. So in this way, we separate u and p degrees of freedom. Okay. Other approach is we combine them all together like u1x, u1y, p1, u2x, u2y, p2, and so on. Okay. So we can do either way. It doesn't matter how we do, but the approach I am following is helpful later when we use a different type of element. Okay, so let's stick to this approach. So what I'm going to do, so I'm going to separate velocity degrees of freedom and pressure degrees of freedom. So that is why we have the separate matrices KU, KUP, KPU, KPP, and we have okay, FU, FP. Right, okay. Okay, so in order to again, so at this point, it would make more sense to start writing the code in such a way that we can easily extend it to elements of different sizes or different shapes. Okay, for example, so if you want to use a 9-noded element, then it should be automatically able to address that. Okay, so what I'm doing now is, so for velocity, so here how many nodes are there for velocity? Okay, so for this element there are 4 nodes, and for pressure also there are 4 nodes. Okay, we can hard code it, but by calculating it based on the node numbers, we can automate it for arbitrary elements. Okay, so here I am calculating the number of nodes per element for velocity and nodes per element for pressure. Okay, as you will see in the next parts, so these can be different, but for this part, okay, both they are the same. We have 4 nodes for velocity, we have 4 nodes for pressure, but note velocity has each node for velocity has 2 degrees of freedom. That is why NDY of number of velocity degrees of freedom per node is 2. Okay, and then we calculate the size of the stiffness matrix for velocity degrees of freedom. That is the KUU matrix. Okay, so n size gives the number of nodes. Okay, number of nodes per element for velocity multiplied by the number of degrees of freedom. So we get the size of the stiffness matrix KUU. Okay, and to automate it further, so what I'm doing, instead of h1, h2, h3, y1, y2, y3, I have now arrays to store those. Okay, so the x and y coordinates. So the advantage of doing this is we can easily pass it to another function, or we can automate the calculations. Okay, so we know the node numbers, we know the coordinates of the nodes, we can extract the corresponding nodes, and the first one gives us the x coordinates and the second column gives us the y coordinate. Okay, so here again it is not completely automated. So for 4 noded element, we use 4 gross points. Okay, we can automate it further depending upon the number of nodes per velocity. Okay, you can do it on your own later. So number of gross points is 4, and what I have done, I have created a function get gross points quad for quadrature. So what this does is it gets an NGP, number of gross points, as input. Okay, and then it gets the number of gross points from 1D, and then it calculates the number of draw point, the draw point coordinates for 2D. Okay, I will share these functions with you. Okay, so we did the number of we did the draw point coordinates and weights, and this element type equal to 2. It is a flat variable for quadrilateral elements. Okay, so using such flats, we can automate the code for different types of elements. Like for example, if I say element type equal to 1, I can add a triangular element. Okay, okay. So these are the preliminary data that we need, and I'm initializing the matrices, the individual matrices. These are the element matrices. Okay, we are in the element stiffness calculation subroutine. Okay, I'm initializing all the sublots. Okay, so KUU, KUP, KPU, KPP, FU, FP. Note the difference in sizes. KU is of size n size by n size. KUP, KUP, it should have the same number of rows as U, and number of columns would be the number of degrees of freedom in pressure. So that would be 4. So number of nodes per element for pressure. Okay. So similarly for KPU, KPP, okay, and so on. For FU and FP, okay, it follows the same logic. And then we define some variables for storing basis functions, basis function matrix for velocity, gradient matrix for velocity. Okay. And du divergence matrix for velocity. Okay. So these are the matrices we know we need to calculate the stiffness matrices. Okay. So GU, DU, NP, NU, and so on. Okay. And then NP for pressure, GP gradient matrix for pressure. Okay, we have defined all the variables. Okay, all the arrays. Now we loop over the draw point, and at each draw point we get the parametric coordinates. Okay, those j and eta variables. Okay, and then we pass this parameter array to this function, compute basis function study. So where where we calculate the Jacobian, we calculate the derivatives and so on. Okay, so here again, like this is a way of automating the code for different elements. Okay, our element type equal to 2, so it goes to the quad function and it calculates the basis functions and their derivatives with respect to local coordinates u1, u2, and then it calculates the Jacobian using the node coordinates. Okay, and then it calculates the derivatives with respect to physical coordinates x and y. Okay, so this was all we were doing inside the element stiffness matrix subroutine, but by making this into a function, we can simply call this function in other subroutines, other stiffness matrix calculations. Okay, so in this way we avoid like duplication of the code, and it's easy to maintain, and like it is less prone to bugs, because if you keep writing the same code, it's easy to make mistakes. Okay, so we simply call it as a function. Okay, and then so we get the Jacobian, the determinant of the Jacobian, and if we multiply it with weight. Okay, so this is our current area or volume. Okay, and then we prepare our matrices of basis functions, okay, and their derivatives. Okay, so first is nu, then gu, and then du, np, jp. Okay, so here we prepare these matrices. So here, okay, so this is our nu matrix. Okay, and this is our GU matrix, and this is our DU matrix. Okay, and this is our NP matrix. Okay, so I also have GP matrix, which we will need in the future. Okay, right. Okay, so we prepare these matrices. Then once we have the matrices, then we can use the expressions for stiffness matrix, these plots. Okay, mu multiplied by GU transpose G multiplied by D volume. Okay, mu GU transpose G multiplied by D volume. Okay, GU transpose GU. Okay, and for KUP minus DU transpose NP. Okay, KUP minus DU transpose NP multiplied by D volume. And for KPU, NP transpose DU. Okay, NP transpose DU. We don't have KPP. We are initializing it already to zeros already. So we don't need to do anything here at this point. Our KPP is 0. It remains 0. And if we have any positive body force F, okay, for this, the first term. So, okay, then we need to calculate this over the element. Okay, so a nu transpose F. Okay, so in this way, okay, so we calculate the element stiffness matrix and force vectors. So all the 4 blocks of the element stiffness matrix and the 2 blocks of the force vector for the steady Stokes equation. Okay, so this is a fully coupled system. Okay, we are solving for velocities and pressures together, that is at the same time. Okay, this is a fully coupled system. We we also call this as a monolithic approach because we have one full big monolithic matrix. Okay, so we have our stiffness matrix, right? So all we need to do is for each element in the mesh, we have to pass this node coordinates, the element node connectivity, the viscosity, and the force vector, the body force vector. Okay, and then it gives us KUU, KUP, KPU, KPP, FU, FP. Okay, so we loop over the elements, we get these values, we assemble them, we solve them. Okay, so that I'm going to show it in the next part.